In the first problem, we're going to determine the molar mass using an osmotic pressure measurement. This is common for large molecules. If we take the equation for osmotic pressure, we first want to isolate the expression for molarity, molar concentration. So we manipulate the equation and we calculate the moles per liter we have for this particular molecule of unknown molar mass. We divide the osmotic pressure, which is given in kilopascals, by the constant R and the temperature in degrees Kelvin. Before we go any further, we will do the math to determine the moles per liter of this solution in the unknown molar mass hemoglobin. Check the units, make sure that we've used the right constant R, and we are left with moles per liter. Next thing we do is determine what we need for molar mass. Molar mass, remember, is just the mass of a compound divided by the moles, the grams per mole. So we are already given the grams we have of this particular molecule, 35 grams. To determine the moles, we'll take the molar concentration, which we calculated above, and we will multiply that by the volume of this particular solution. The volume, remember, was 1 liter. So in the denominator we have moles, and the numerator we have grams. So now we just again do the math, give us an amount in grams per mole. So this is the molar mass of this particular hemoglobin molecule. Note that it's very large, as is typical for molecules that we use the osmotic pressure to determine the molar mass. The next part of the question is asking you to think about whether the freezing point depression would also be a possible way to measure the molar mass. And so what we'll do is we'll take the sample from above and we'll calculate what the freezing point depression would be for this particular sample. How low would the freezing point be driven by this particular sample? So to get the freezing point depression, we need the molality. So we start with the molality, moles of solute divided by mass of solvent. To get moles of solute, we have a mass, the mass of that original hemoglobin sample, again, 35 grams. We divide it by what we have discovered to be the molar mass. Remember that large number. And so this altogether would give us the moles of hemoglobin. In the denominator, we should have mass of solvent, and that's a little tricky because all we know is that we have a liter of solution. So we're going to make an assumption here because we just want a ballpark figure for the delta T. So we're going to assume that that whole liter of solution is in fact mostly solvent. So we're going to say we have a liter of water. We're going to convert the liter to milliliters because the density of water we have is in grams per milliliter. We need the mass of solvent in kilograms in the denominator, so we finally convert the grams to kilograms, and we end up with the approximate molality of this particular solution. Note the units, we have moles per kilogram of solvent. So now we put a number to this, and this number is moles per kilogram of solvent. We're going to put that back into the expression for delta T. We're going to use the freezing point depression constant for water in degrees Celsius per molar. We multiply that by the molality of the solution, and we get a change in freezing point of approximately 10 to the minus 3. This would in general be too small to measure, and therefore this would not be a good way to determine molar mass.